Okay, this is chapter 13, lecture 10, which we would have done live. Uh, I would like to go through 3 example problems of energy, and after that, on Wednesday, we will pick up with a little bit of energy, and then we'll talk about impulse momentum. And the objective of impulse momentum is the third idea. We have F equals ma, we have energy, and then we have impulse momentum, all of those which emanate from Newton's second law. So I would encourage you in this lecture, since it's a little different than having a live lecture, I'm going to be doing 3 example problems. I would look at them. I would take the time to attempt them yourself and work as much through them as you can before you watch me do the solution. I guarantee you that's going to be much more beneficial to your understanding than if you just watch me do the solution. And I know some of you are struggling with the material. And so my hope is that by repetition and working through it, struggling through it, that will help you understand it better. And again, I encourage you guys to work together with different people and have study groups. That's really important to do in this class. All right, so let's get started. So the first problem is going to be this one, roller coaster problem. So here we have our roller coaster A. At A, it starts, rolls downhill until it gets to B. So we know from looking at this initially that it's going to be an energy problem. Now, even though we weren't in energy per se, this would be a good energy problem because we see we have a change in height, and the only force that really is acting on this whole system is gravity. So using energy seems like a good way to approach it versus F equals ma or impulse momentum. So you're going to come down, you're going to hit the bottom B here, you're going to go around the track to D, and then you're going to continue. So this question has 2 parts. The first is determining the force. So what is the force on the passenger at point B? And that's, of course, we know there's going to be a tangential velocity, and there's also going to be a normal acceleration pointing towards the center of the circle, and that's what we're going to use. So we're going to need to use a little bit of F equals ma to figure out what the force is on the person, and then we're going to use energy to figure out how fast they're going. They're going to go around the circle, going to end up at E. So we want to know what the force is at B and D, and then we also want to know what is the minimum curvature, because we know that the greater the curvature, the more the acceleration, the more apt you are to fly off the track, so to speak. And so we're assuming that it's just a cart sitting, not doesn't have any kind of way of holding itself to the track other than gravity. So we want to make sure it doesn't go flying off. Anyway, so that's what we're going to do. So I would encourage you at this point to pause the video, set it up how you would try to go about solving it, and then do as much as you can. And if you get stuck, come back and look at the solution. But if you can work through it all yourself, then you're going to be doing well. All right. So I'll pause it now for you, and then now I'm back because you unpaused, and let's go ahead and talk about the solution. Okay, so here's the solution. So we start here, roll down. So we know that we're going from A to B. We have T1 plus U1 to 2 goes T2. The initial state of T1 is 0 because our velocity is 0. U1 to 2 is just going to be mgh, and then our final kinetic energy is 1/2 mv squared. Now we know we can simplify that to be v squared equals 2gh, and we can solve for velocity. I'm going to leave it like this because we know also that if we want to find the acceleration normal, that's going to equal v squared over rho, isn't it? Now, remember the objective at B is to find what is the normal force. So we're going to need a free body diagram. So let's just say this is the free body diagram of the cart and the rider. We know that it's going to just have mg and then the normal force acting on it, normal force at B. And we know that's going to equal the acceleration of MAN towards the center of the circle. So if I go ahead and substitute in here v squared d2gh, I get 2gh over rho, but I know that h is 60 feet. I know r is 20, so I can also write this as an equals 2g 60 all over 20. So that's basically 3 times 2, or 6g. Now you could multiply everything out and make it, but this I think is a little easier because now we see the normal force is basically 6g. So if we come back over to our equation, we know that if we sum our forces, we're going to get sum our forces equal to MAN. Then what do we have? We have the normal force of B. So we're going to assume, again, our coordinate system is plus plus, like that. So NB minus MG equals MAN. But we know that's 6G, right? So it really says NB equals MG plus M times 6G. All right. And so everything essentially cancels out, because not everything cancels out, but what I mean by that is we get NB is going to equal to 7 mg. Now, we know that mg is 160 pounds, so that's weight. So really the normal force is just equal to 7 times 160, which gives us a value of about 1120. So our normal force is equal to 1,120 pounds. So to review, what did we do? We said we found v squared equals that. We could have found velocity, but because we know v squared over rho is our acceleration in the normal, we left it as v squared. Then we said a normal equals 2g 60 feet over 20 feet. That gave us 6g. So then when we did our sum of our forces equal to MA, we had normal force of B minus MG, mass in A. MG plus M6G gives us 7. So basically 7 times the weight gives us our normal force of B. And there we have it. So not too bad. So now we have to do it for the top at point D, which is up here. And that's going to be very similar. The only difference is now gravity isn't going to be helping us. It's going to be, gravity isn't going to be adding to it. It's going to be subtracting to it. So we can almost anticipate ahead of what that's going to look like. But go ahead to end, like I said before, is hopefully you've worked this far. But if you haven't, take this, and now that of what you know of this, if you struggle to get this first part, go ahead and try to figure out what the normal force is going to be up at D. And so that'll be a little more work just in case you didn't understand this. And then we'll go over that. So if we're at the top of the roller coaster, we notice that the equations still work. The difference is a negative sign in here, but also the fact that now you've lost a lot of your kinetic energy, right? Because if you think about this, if this is a radius of 20, 20, 40, and your height now is only 60. So height 60 minus 40 gives you only 20 feet of kinetic energy. I'm sorry, 20 feet of potential energy converted kinetic, whereas before you had the full 60. So if we look at the equation, we still know our normal force, right, is equal to v squared over rho. So if we go ahead and put in what we know that v squared again was what? 2gh. Well, h equals 20 now, because the height is essentially height equals 60 minus 40, right? So the height's only 20. So what we end up with is the acceleration normal is going to be equal to 2g times 20 over 20, or essentially the whole thing equals 2g. That's all the acceleration we have. Our free body diagram has normal force of D, and of course mg is still going down, and that equals ma normal, because again we're at the top of the circle, so it's pointing down. So in that case we have nd plus mg equals man, but we know that that's going to be m2g, so nd plus mg equals m2g. Subtract from both sides, so therefore n at d just equals mg, or 160 pounds. So with this configuration, as the individual goes to the top, they feel as if they were just sitting on the ground at 1g. Oops, sorry. There we go. Sorry. So we have nd, mg, sum of the forces equals man, and then we move it to the other side and we get mg. All right, so hopefully that's pretty clear. So the last thing we want to do is figure out, back to our diagram, is how far off, how big rho needs to be based on when we come off of here, we're going to come back around. So we know we're going to have a certain velocity at this point again, which, because there's no friction, we know that velocity is going to be the same as it was when it first entered the circle. So how is that going to affect this? And that's something that's a separate problem. So if we're trying to figure out this radius, first we note that from the drawing that this top peak here is at the same height as this middle point here, which I think was C. So we know that that distance there has to be 40 feet. That's how high it's going to be, right? Because it started out at 60 and then to 20. So the difference, the potential energy is 40 feet total. Now, the other thing we know is that if this is just going to stay here, that means our normal force is 0, right? That's how we decide whether it's going to fly off the track or not, when the normal force goes to 0. So that's quantitatively how we know that. So if we go back and we again look at point E, okay, so we know in this case that just like before, we're going to have our object. And so this time we're going to sum the forces, and just for convenience, again, we know that up is going to be positive. So we're going to say that mg is, in the past we said it was positive, sorry. We said it was positive, but we're going to switch that. And the reason we do that is if we make down positive, then we know that our acceleration is going down. And that's actually what we did up here. We made down positive. And that's why these are both. It still works either way, but it makes it a little easier. So we made down positive in this case because the acceleration is down. That is also, so the normal force, if we say mg and normal force plus mg equals ma, normal force goes to 0. And we know that an is going to be equal to 2gh over rho. Now remember, what is h over rho? We essentially have, because we're trying to solve for this. So if we simplify this, it becomes mg equals m times 2gh all over rho, but m's cancel, g cancels, and if we look at 2h, h is 40. So we have rho equals 2h, and if h equals 40, then rho must equal 80. Okay? So again, you could replay this, but just to explain it, and again, you have your cars coming up here. We're at that peak. So we have our height, or our kinetic energy, is from 40 feet of height. So we go in and we make our free body of this. We say everything's pointing down is positive. And we say N plus mg equals MAN, which is just our normal equation. N is 0. So we have mg equals m. And then we know that AN is 2gh over rho, right? V squared over rho, which we know 2gh is the same. So we cancel, move it over to the other side. We have 2h. But since we know h is 40, we know rho is 80. So that makes sense, because depending on how high up this was here, that's going to determine how much energy, how much speed you have here. So we know that if this had come all the way back up to the top, it would have just barely got to the top at a velocity of 0, just like the example in class. All right. So hopefully that makes sense. Hopefully you're able to work through that with minimal assistance from this. But let's go back and go back to this. Now let's look at the second example. All right, so this is the one I wanted to do in class, but we ran out of time. And so here we have a energy problem again. It's going to be a force times distance type problem. So we know that think of it, the car's driving, it's at 65 miles per hour. It hits the barrels. The barrel's resistance, or force over distance, is given by that chart. So it shows that for the first 5 feet, it gives you 18,000 pounds of a resistance per foot. And after 5 feet, it jumps to 27,000. And after 14 feet, it jumps to 36,000. So we are going to assume in our initial, we're going to think, well, maybe because they give us 5 and 14, and that's a lot of force, that will be within the 14 feet. So if we're not, then we would have to go back and add another term. But if we are within the 14 feet, then it'll make things a little easier. Now, so let's see, how are we, first off, just like before, is I would go ahead and try to set this up. You know, it's going to be a kinetic energy. So you know that you have 1/2 mv squared of your vehicle minus force times distance equals 1/2 mv squared, which is 0. So T1 plus U1 to 2 equals T2, or essentially T1 equals negative U1 to 2, because all of the energy absorbed is going to take away all your kinetic energy. So the only question is, how do you set it up using this? So go ahead, do your best, solve it, and then come back for the solution. So here's our object. We know that the weight and the normal force, since they're perpendicular to the direction, do no work. So really it's only the force times its distance. So the initial velocity is 65, which converts to 95.3 feet per second. We know that T1 plus U1 to 2 essentially equals 0. So first off, let's figure out what T1 is. So T1 is just equal to 1/2 mv squared, or T1 equals 1/2. And we know that the mass, or the weight of the car was 2250 pounds. So we know that's going to be 2250 divided by 32.2 because we need mass. And then multiply that by our 95.3 feet per second, and that's squared. Okay. So there's the pounds. So here's our slugs. And so we end up with this equals to 317,530 foot-pounds of energy. That's how much the car has. Okay. So if we look at U1 to 2, based on the diagram, and if you need to pause and look at the back of the diagram, but essentially the diagram does this. It has a step function, so to speak. So the first 5 feet, that's at 18, right? So U1 to 2 equals 18,000 times 5 feet. We're going to assume it's going to absorb all that, and then plus, and then it jumps up to 27. So we're going to say it's plus 27,000 times d minus 5. Now, the reason we have to say d minus 5 is because we think it's going to end up somewhere here. And we're not going to just say d because we have to subtract off that since that's already accounted for. So if it was all 27,000, we could just put d. But effectively, by saying d minus 5, we're saying that 5 feet of it does not have the 27,000. So we have to subtract off that because we're adding that. That's all it is algebraically. So we end up with something that looks like 90,000 plus 27,000 d minus 135,000. All right. Or effectively, this equals 27,000 d minus 45,000. So we have, this is our relationship. So now what do? We go in and we say T1, right, plus T1 basically equals U1 to 2, or we can write it as 317,530, right, foot-pounds equals 27,000 pounds times d in feet minus, that's the unit, and then minus 45,000 foot-pounds. So now the unit's in feet. So we end up with solving, we get d equals to 13.43 feet. So we are under the 14 limit, but let's say that we didn't get that. We got 17 feet. Okay. Well, then we'd know that we passed this limit. So what we would do is we'd go back and we'd say 18,000 times 5 feet plus 27,000 times 9 feet. And then it would be the upper, after this, it goes up to 36,000. So then you would add the term here that said 36,000 times d minus 14. Does that make sense? So you would have had a full number here, and so that way you would subtract off it if it had gone all the way. So maybe it's a big semi truck, you would have had to have done that. All right. Okay, so part B asks for what is the maximum deceleration. So Well, we know that the maximum deceleration is essentially the maximum force equals ma, and the maximum force is at 27,000 when it hits here. And so we know that if we say part B, F equals ma, then we know that 27,000 equals the mass, 2250 divided by 32.2 times A. And so A equals about 386 feet per second squared. So if you think about that, 386, that's about almost 12 Gs. So probably going to pass out depending on, but that assumes, again, the assumption with 12 Gs is that this is a rigid body, that the truck is a rigid body, or I'm sorry, the car. So in reality, if this was a real crash, then some of this energy would be absorbed by the plastic deformation of the vehicle. So as the car drove through these barrels of water or whatever they are, then the car would crumple, and that crumpling or plastic deformation of all that steel, plastic and whatnot, would absorb energy, which would then not be transferred to you. That's why newer cars are safer than cars from, say, the 50s or 60s that were big tanks, because yes, you'd hit a wall and nothing would happen to the car, but that just meant all the force was transferred to the person. So ideally, the best situation is have the car completely collapse around you and become, so you're like in a big tinfoil ball. Anyway, we digress. Good. So hopefully you guys got that no problem. So we have one more example. And that's this one. So that's a little different. It's a spring, but it also combines the gravity. So we have this 1 pound collar that's here, and it's attached to a spring, which we're given the constant for. And we know it's held at A. And so we want to determine the speed of the collar and the normal force as it passes through B. So I guess what it's going to do is it's going to go from here and it's going to go down. So we know it's going to have gravitational potential energy that's going to help add energy to the system. Spring is going to relax, which is going to add some, and it's also going to convert that to kinetic. So spring and gravitational to kinetic. So I would go again, draw the diagram. First, figure out how much is the spring stretched. So for one thing is, based on, because even though it's drawn up here like this, it starts at A. So A, you know how far it is, right? 7 plus 10, 17 inches. And so you know that if it's undeformed length of 5 and it's stretched to 17, then it has a 12-inch deformation. When it's down here at B, you can use triple triangles to figure that out. And then you'll know how much it's deformed there. So basically, you want the difference in deformation between A and B is going to give you how much spring elastic energy is converted to kinetic energy, coupled with how much gravitational potential energy you gain by dropping from A to B. So again, if you can do this all on your own, then you're in really good shape for energy. Go ahead and take a stab and then check out the solution if necessary. So first, let's get our spring distances correct. Now, if we look at the layout, this is point A, this is point B. So 755, that's a total of 17 inches. But we know that the springs relaxed at 5. So the length of A is going to be 12 inches, essentially 17 minus 5, right? So 12 inches. And then down here, we know that if this is 12 inches and that's 5, then this is a 5, 12, 13 triangle. Therefore, this is 13 inches. So 13 minus the relaxed state is 8. So this is important because we have 10 pounds per foot. So really, length of A equals 1 foot, and length of B is 2/3 of a foot. And if you don't change that, you're going to get messed up. So make sure that your units are correct. Seems like a trivial thing, but it's easy to get ahead of yourself. Now, one thing that is in the book, which we didn't mention, is there's another way to write it, which I did. Actually, I wrote it on the board, is when you can write TA plus VA equals TB plus VB. And you'll recall that this is just what is the condition at A, this is the condition at B. Remember the TA was representing the kinetic energy, whereas V could be either elastic or gravitational. So this is just another form of the general energy equation. Nothing's new. We're just making sure that we account for energy at the beginning and energy at the end. So first off, we know that at A, there's no kinetic energy. We start at A at rest. And then we want to figure out what is our elastic energy at A. So if we think about, if we break this down, we're going to have VA elastic, and that's just going to be 1/2 kx squared. So if we plug that in, we know that we have essentially 1/2 of 10 times 1 squared, which is 5 foot-pounds. So that's how much potential spring energy we have at A is 5 foot-pounds. Then we have to look at it as, if it travels from here to here, how far is it dropping? So we know it's going to be an MGH for that. So we'll figure out what the MGH is, and then essentially, excuse me, be able to add everything together. So we have the 5 foot-pounds here. And then what are we going to add to it? Well, since this is dropping down here, that's also energy added to the system. So let's think about it. We have 5 foot-pounds of energy on this side, on the left side. And then we're going to add to it the MGH, right? So from A to B, that's going to be what? It's going to be 1 pound, right? MGH, 1 pound times 5/12 of a foot. So that's all it's dropping is 5 inches. And that's going to give me 0.4166 repeated foot-pounds. So I'm going to add to that 0.4166 and so forth. So again, and I find this easier than just plugging in numbers up here because I think it's easier to understand if you see like a balance sheet. So we started with A, we had so much potential energy, we had 5 foot-pounds, right? So 5 foot-pounds at here. Calculated that by multiplying 1/2 10 times 1 foot squared. Then we dropped down to here. So we had that for 0.4166 foot-pounds. That's from the gravitational. Now, if we had gotten to this point and the spring was completely relaxed, then we know that this energy would have all been converted to kinetic energy. However, we know that when it gets to here, it still has some. So we can say this is going to equal, and it's going to equal what? It's going to equal 1/2 of 10. And then how much is left? We said 2/3, right? 2/3 of a foot. So that's got to be on this side. So effectively, you'd subtract it from this side because that's how much energy is left. So the net spring energy is really 5 minus that. And that ends up being about 2.222. So if we rewrite this, we have 5 plus, all in foot-pounds, 0.4166 minus 2.222, which is this value here. And so spring energy, gravitational potential, remaining spring energy, and then all of that would equal what's the velocity. And so for my velocity, of course, I'm going to use what I've written down here, 1/2 mv squared, where I have 1/2. That's the reciprocal of 32.2 because I only have 1 pound. So 1 over 32.2 is that number. That's how many slugs I have. So when I multiply by 1/2, I get that. So this is going to equal 0.015528 v squared of b. Sorry, it's getting a little. So now we just solve for b, and we know our value for velocity of b at that point is just equal to 14.34 feet per second. So hopefully that makes sense. I would, if you're not sure, go back, rewind, listen to what I had to say again, because I think, if looking at, again, strictly from energy, if you do that, you should be fine. All right, so the second part of this problem is to find the normal force, or how much force is created on the collar. So the collar is like a cylinder on a ring. So first, of course, we're going to draw what does the free body diagram look like. And presto, there's the free body diagram. So if we're looking at the collar, so remember the collar's down here now, the collar's going to look like this. So again, it's riding on a ring. So the normal force is going to be pressing up, mg down, and then the force of the spring is going this way. Now at this point, the spring force that we're interested in, since we're looking for normal forces, we only want the vertical part. So the vertical part, we know is just going to be the force of the spring times the sine of alpha. Well, we know that the sine of alpha is the ratio of opposite over hypotenuse, or 5/13. So no need to find an angle and then go back and take the sine, because if we find the angle and then take the sine, we'll get 5/13. So we'll just leave it like that. Also, we want to know what the force of the spring is, because that's pulling up and going to cause normal force. So we know that the force of the spring is 10 pounds per foot. We're at 2/3 of a foot, so we have 666 pounds, evil pounds. And then our free body, we do have acceleration tangential, but we're not worried about it because we're only interested in the normal force. So if we look at the normal, it looks like this. So now what we need to do is just write our equation. So we know that the sum of the forces in the y equal ma in the y. That's nothing new. So what is that going to look like? It's going to be fs times fs sine alpha. And again, we're assuming up is positive, sine alpha. And then minus the weight plus the normal force equals MAN. So now let's do some substitution. We know that AN is going to equal MV squared over rho, which is just going to equal 0.031056 times our velocity, which was 14.34. Right, so this is just the mass, 0.310. All right, so hard to read. 5. Actually, let's make it bigger. 0.031056, and then multiplied by 14.34 squared. So mass, velocity, and then all that divided by 5/12. So this gives us a value of about 15.33. So that's what we're going to say is our MAN. So MAN including, sorry, it was this MAN equals this. So MAN, this part equals 15.33. So then what do we have? If we rearrange, we know that normal force equals MAN plus W minus the force of the spring sine alpha. So that equals 15.333 plus 1, and then minus 6.666 times 5/13. And that's it. And that's all we have. So we figure out normal force then is about 13.77 pounds. And there you have it. Sorry. All right, so backing up. So we sum the forces. Here's our diagram. Sorry, not quite the same as the whiteboard. So we found out our radius was 5/12. We know that the angle is 5/13. So we know our spring force is this. Sum of the forces is spring force times sine alpha minus W plus N. W is 1 pound. Sine alpha, so that is just 666. Normal force, what we're solving for. MAN is up here, MV squared over R. Weight in slugs, velocity squared over the ratio, or the radius, 5/12. Plug all that in down here. The 666 was that. And we found that with 2/3 because that's how far we'd stretched it. But the 5/3, this is equal to sine of alpha. All right. And we get that. That's it. So again, that should hopefully help you understand energy overall. We had spring and gravitational, but again, the whole process, you could probably write it out in simpler terms, but I like to go through everything to show you where everything came from. So hopefully this helps. And you were able to do most of these by yourself with little effort. And again, that's the nature of the class, is how well you can do these on your own and how well you recognize what's what. So this is energy. When we come back on Wednesday, we'll probably talk a little bit more energy, and then we'll jump into our impulse momentum. So I hope that helps, and I will see you guys soon. Thank you.